Hello everyone, my name is Lasantha Senanayake and I'm here to present our research on language models as narrative planning heuristics. So first of all, let's talk about what is narrative planning. In interactive narrative environments like games and training simulations, often need to maintain a coherent storyline while adapting to user choices. Narrative planning is a tool to generate structured stories. Traffic Stop is a virtual reality de-escalation training simulation for police officers that uses narrative planning, which is created in our lab, where the story and the behavior of non-player characters are intelligently adapted based on the player's actions. So, in this project, we use something called Sabre, and Sabre is narrative planning system that models both the intentions of author and intentions and beliefs of each virtual character. A traditional planner can ensure the system level goal is met, but does not reason about agent realism. But Sabre is a narrative planning system that models both the intentions of the author and intentions and beliefs of each virtual character. Sabre is a forward state space planning algorithm that searches the story graph. Here in Sabre, the search begins in the initial state, which describe the initial state of the story, and follows edges, which are actions, forward until it reaches an acceptable terminal state where the author goal is achieved. But every action taken by an agent to come to this terminal state must make sense according to that agent's individual intentions and limited and possibly wrong beliefs. And accounting these constraints, Sabre gives us a solution. We have used 11 different domains that we benchmark Sabre on. Out of these, I'm going to choose modified version of a grandma problem to give you some examples. In this modified version, there are 3 characters in this story. The first character is Tom. He has a coin and starts at his grandma's cottage. As I told you earlier, each agent in this story has a goal or multiple goals that needs to be achieved. Tom wants to heal his grandma by being at the cottage with the potion. And the second character is Merchant, and the merchant's goal is to have many coins as possible without being a criminal. And the third character is the bandit, and the bandit needs to have many coins as possible, and bandits start at the bandit camp and has a sword which can use to slay people. There's a special agent in the Sabre planner, which is the author, and the author has 2 goals. Either Tom needs to die in the story, or Tom needs to bring back potion to grandma's cottage in order to end the story. So here are two of many plans that planner can come up with that achieves author goals. In the left one, Tom brings back the potion, but in the second plan, Tom dies. Both are valid plans, but it's not that simple, since planner needs to argue that consenting characters to these actions act believable according to their beliefs. To explain this point, let me take the second plan where Tom dies, and let's focus on one action where Bandit walks to the crossroads. Here the planner needs to plan for the bandit to find out why would bandit walk to the crossroads. Planner looks into the bandit's beliefs. Here the bandit believes that Tom is at the crossroads and Tom has a coin. So Sabre plans for the bandit according to bandit's beliefs, and the planner plans for the bandit checking by taking available actions. Updating beliefs as taking actions to find a plan for the bandit to achieve bandit's goals. So here the planner identifies that by taking the action walking to the crossroads, the bandit can achieve the goal. So since bandit walking to the crossroads can lead to plans where bandit can increase his utility by achieving bandit's goals, so here is why this makes it planning planning complex than classical planning. This needs to be done for every action according to agents' beliefs, which are also updating as the world around them changes, according to all the actions taken by each agent. This story seems very small and simple with small plans. You might think that this has very small story graph too, but since the agents in the story can behave any way according to their beliefs, this story has a story graph with millions of nodes or states. And searching through that story graph to find a solution or a plan is very hard. To search through this mess of a graph, we use heuristic search. And there are three classical planning heuristics that we specifically going to talk about. H+, Hmax, and relax plan heuristics. All three heuristics share a common approach of solving a relaxed version of the planning problem and using the size of a relaxed solution as an approximation for the distance to the goal. But these are not specifically designed for narrative planning, hence they can't grasp the concepts like the beliefs or motivations. So our idea is that can LLMs be used as heuristics in narrative planning? Because unlike classical heuristics, LLMs can suggest explained actions and account for character beliefs and motivations. So the problem we are trying to solve is asking an LLM to complete a story so as a better heuristic than those used by classical planners. In order to do this, since prompting an LLM million times is very time consuming, we first sampled 1,000 nodes which are known to have solutions which are not terminal states by using exhaustive breadth first search. And each of those sample states have data stored about the simulated world, like character beliefs, current state of the world, available actions, etc. We created a zero-shot prompt template that provides context about the story so far and ask for the next actions to achieve the author's goal or the goal of the character who we are planning for. And we can break down this prompt into 7 parts. And here's an example of a prompt that we use. The problem statement and the current state have been shortened to fit into the screen. And first section is the task section. In this section, we tell the LLM its purpose is to complete a story. This text is same for every prompt across every problem. The second section is in this problem section of the prompt, we list all the objects that can exist in the problem and the properties they can have, introducing each character and explain their goals and describing kind of action that can occur. And this text was written by hand for each problem and was the same for every state for that problem. And the third part is previous sections. In this section, we list any actions that have occurred so far, translating each into a natural language sentence. The story so far is described from the perspective of the character who is planning. And the next section, in this section, we describe the current state, giving the value for each fluent as a natural language sentence. The current state is described from the perspective of the character who is planning. To prompt LLMs properly, we converted all the fluents and logic which are written in syntax form in the states into natural language sentences programmatically. Next, we instruct the LLM to complete the story using a few actions as possible and without adding new elements or actions to the problem. This text was the same for every prompt across every problem. And then we tell the LLM which of the characters goals to complete. And finally, we ask LLM to format the output in JSON format. Actually, we created 2 types of prompts for each node or state, one using natural language, as you can see here, and the other one is using Sabre syntax to check whether LLMs can understand this syntax and follow the syntax to give our valid plans. But we found that outputs from these prompt variations are very verbose. Like you can see here, sometimes providing plans with 20 to 30 steps. So we created additional 2 prompt variations out of these, which uses limits to guide the LLM to give some idea what is the maximum length of the plan that we are expecting. So we added new sentence at the end of these prompts, which keeping the story complete, a smaller story is preferred. Suggested maximum number of the actions in the story is the number. So here's how we calculate this maximum number of steps. And this predefined maximum is based on the depth reached during that problem's breadth first search. And we use ChatGPT for O-Mini to this test, and we set the temperature all the way down to 0 to get deterministic answers. And from this model, we got plans in natural language for natural language version of the prompts, and for the Sabre syntax versions, we got the predictions in syntax version. However, the actions that were expressed in natural language sentences for the natural prompts, and occasionally as incorrectly formatted Sabre actions for the syntax problems, we need to translate the LLM's plans back to Sabre plans. So for this, we used ADA text embedding models and used cosine distances to find the closest correct actions using this model. What we do here is that we find the closest Sabre action predicted by the LLM. So here are the results we got for those 11 domains that I talked about earlier. And first, the length of the LLM predicted plans were compared against the length estimates of 3 classical heuristics when evaluated on the same states for these same goals. And when we compare heuristics, we weighted them to further fine-tune them to specific domain using an epsilon value ranging from 0.1 to 2. And here are the maximum mean squared error values after fine-tuning epsilon for each problem. And here, lower values are better, and in the secret agent domain, syntax limit version was able to beat all the classical heuristics. And in space, pressure, and fantasy problems, LLM heuristics or a version of it were able to beat at least one of classical heuristics. In Raiders, Jailbreak, and Bribery domains, LLM versions did very poorly, and in other domains, LLM versions came close. When evaluating relaxed plan heuristic, we can compare both the length of the relaxed plans and the content of those plans to the plan generated by the LLM. So we measured whether the relaxed plans generated by relaxed plan heuristic and the plans generated by the LLM contained actions that were known to lead to a solution. Here in treasure and space domains, LLM versions were able to beat the relaxed plan heuristics predictions. We found that in 2 of these domains, LLM were doing very poorly. In hospital domain, in the Sabre syntax versions, the LLM often misinterprets the structure of actions. It tends to treat actions as functions and try to nest them incorrectly. In the natural language versions of this hospital domain, the problem was that the LLM often provides vague or incomplete actions instead of specifying treatment details. In lovers domain, the poor performance appears to be due to the complexity of tracking multiple characters and objects as well as their locations. We face some challenges as well. The time it takes to call the GPT and the received responses from LLM is very high, and LLMs sometimes provide unpredictable outputs, and LLM's predictions depends heavily on quality of the prompts. So as conclusion, our findings were mixed. LLM-based heuristics show varied performances across different problems, indicating that no single heuristic is universally effective for all narrative planning problems. And also our findings emphasize that potential of LLM-based heuristics, while also underscoring the importance of continued research in prompt design and hybrid heuristic methods to achieve consistent and reliable performance in narrative planning. Thank you. Thank you very much for listening, and here you can find all the code and prompts and results on our GitHub link. Thank you.